Before embarking on any supernatural hunt, it's going to be crucial to locate the elusive entity. Sam and Dean often spend time reading the news to find cases, researching to aid in defeating the entity, eating takeout, and of course living out of motels to fight any supernatural force that they come upon. Recent reports from the Mystic Fall Times suggest that unexplained phenomena are occurring due to chemical reactions in the region. Our mission is to determine if these changes are spontaneous or non-spontaneous, and then figure out how to predict the direction of spontaneity. To kick off the investigation, we'll dive into the fundamentals. We'll first consolidate our knowledge about spontaneous change, and then we'll get into the first law of thermodynamics and enthalpy. This is all going to be the groundwork to help us make these vital connections as we prepare for this hunt. So first things first, what is spontaneous change? A spontaneous change is one that occurs without a continuous input of energy from outside the system. What is the system for us? It's going to be chemical reactions. So this means these chemical reactions will occur without a continuous input of outside energy. I don't have to continually put energy in for the entire reaction to continue to go from reactant to product. Why is that important to say without continuous? Well, all chemical processes require energy. We know that because we understand that all chemical processes require activation energy to take place, right? But once a spontaneous process has begun, no further input of energy is needed. That's why it's considered spontaneous change. Now, of course, if a spontaneous change is occurring in one direction, there will be a non-spontaneous change in the reverse direction. And a non-spontaneous change occurs only if the surroundings continually supply energy to the system. So in this spontaneous, non-spontaneous change here, you must continually add energy in order to go from whatever you're starting with to the product you desire in the reverse direction. So of course, let's get into some examples. We're looking at the Mystic Fall Times, and these are some of the spontaneous and non-spontaneous changes or phenomena that are occurring here. So first things first, heat flow. We're saying if we have something that's 200 degrees Celsius and something that's 100 degrees Celsius, spontaneously, something that's very, very hot is going to disperse to something that's very, very cold, for example. All right, so that is a spontaneous reaction that's going to occur until both of these cinder blocks are the same temperature. That required no extra energy. The heat flowed from a region that was highly concentrated with heat to a region that was lower concentration. Now, in order to go back from these 150 degrees back to the 200 or 100, you're going to require extra energy or work to do that. That is non-spontaneous. I'm going to have to decrease the heat energy here, increase the heat energy here in order to make it look like what it started with. That requires work. Same thing with the wheelbarrow. If it's going to rust, it's just the fact that the metal here is being exposed to air. That is a spontaneous change. It's going to be as soon as the activation energy for this process to happen, it's going to start producing rust. That's spontaneous. But if I want to get rid of the rust is not automatically going to go back and be starting to flake off until it gets back to the metal portion. No, I'm going to have to put in extra energy and scrape off the actual rust if I want it to look like it did initially, right, folks? Same thing with gas flow, right? We have two vessels here, and there's a stopcock. If I open the stopcock, then naturally, spontaneously, these gas molecules are going to go from the area of a high concentration to low concentration until it reaches equilibrium. If I then want to get rid of any gas molecules once they reach equilibrium to look original like it did here originally, then I would have to then put in energy to again close the stopcock to force gas molecules in one direction, right? And then finally, let's just think of like cliff jumping or mountain climbing. You have to run and jump off the cliff, but you don't have to keep on running in order to hit to the water, right? You're just going to spontaneously go from jumping off the cliff until you hit the water. But in order to go back up the cliff, you're going to have to use energy and you're going to have to climb. You're going to have to climb and climb and climb the cliff until you get to the top. So that kind of helps us understand the difference between spontaneous change and, of course, non-spontaneous change. But how can we predict the direction of spontaneity and then use these predictions to help stop the phenomenon of Mystic Fall and, of course, understand thermodynamics even more? Let's continue our investigation by consolidating more of what we know from Chem 101, like the first law of thermodynamics and enthalpy. Let's see whether energy changes using the first law of thermodynamics can predict the direction of spontaneous change. So the first law of thermodynamics is going to explain that the internal energy of a system, which we know as delta E, and also is the sum of the kinetic and potential energies of its particles, is conserved. For us, that system are chemical reactions, right? So the internal energy of a chemical reaction is conserved. And that energy is neither created nor destroyed, but it is transferred in the form of heat and or work. So we can say that our change in internal energy is equal to Q plus W. And Q is going to refer to heat, and of course W is going to refer to work energy. We then can say whatever is not a part of the system is considered a part of the surrounding. Thus, the change in energy and therefore the heat and work absorbed by the system are going to be heat and work released by the surroundings. And of course, vice versa. The heat and work that's going to be released by the surroundings is going to equal the heat and work that's going to be absorbed by the system. We can then go further and figure out the change in energy of the overall universe. How do we do that? We just add together the energy of the system and the energy of its surroundings. When you add them together, that's going to equal a constant, which is simply going to be 0. That is going to give us the total energy of the universe. So we might be saying, wait a minute, how do we go from a system of a chemical reaction straight to the universe? Yes, the laws of thermodynamics do apply to something as small as a system and surrounding and mini universe in our chemical world, as it does to the universe in the real world, right? Our planet system, our human body, etc. All these laws of thermodynamics do apply. And although the first law of thermodynamics is really great at accounting for energy changes, it's still going to lack the capacity to do what we're here for, which is to predict the direction of spontaneous change. And so this limitation arises because, again, the first law of thermodynamics focuses on quantifying the total energy within a system, and of course its surrounding as well. It does not provide any insight on whether the process will naturally proceed in one direction or the reverse. For example, let's say you have an ice cube sitting in your hand. What's going to happen? The heat from your hand is going to start melting the ice cube. That does follow the law of thermodynamics. Energy was not created nor destroyed. All that happened is that you had a phase change here, right? However, the first law of thermodynamics cannot address why the pool of liquid here that's in your hand doesn't transfer heat back to your hand and then recreate an ice cube. It doesn't explain that part. So simply put, the first law of thermodynamics scope is always going to be constrained to energy conservation, and it does not offer predictive capabilities. So we have to continue on. So our investigation and understanding how to predict spontaneous change continues, and we find an article that in the 19th century, prominent scientists believed that the sign of the enthalpy change, denoting the heat gained or lost, right, at constant pressure, might hold the key to this prediction. According to this perspective, exothermic processes, where delta H is less than 0, will naturally be spontaneous, while endothermic processes, where delta H is greater than 0, will be deemed non-spontaneous. And our goal is to verify whether or not this is true. In other words, if we can understand that exothermic processes tend to be spontaneous, are there any endothermic processes that are also spontaneous? And if there are endothermic processes that are also spontaneous, then again, we cannot use this variable to help us with our prediction. So let's first talk about exothermic processes. So exothermic processes where delta H is less than 0 are spontaneous, okay? This can include freezing and condensation at low temperatures. It also can include combustion or rust. These are all going to be processes that release heat energy when you're going from reactant to product. And guess what, folks? We also see that spontaneous change occurs with endothermic processes where delta H is greater than 0. Processes like melting or vaporization, these are endothermic and these are spontaneous. Processes like dissolving soluble salt, these are also endothermic and spontaneous. Or even mixing solid. For here we have our barium hydroxide that's hydrated mixed with ammonium nitrate here. When these mix together, they're going to spontaneously form a very, very, very cold mixture. So cold, in fact, that the beaker freezes to a wet block. And you might be asking, well, why does this happen? Well, because of this spontaneously absorption of heat from the surrounding causes this reaction to occur. So yes, at certain conditions, we can see delta H, no matter if it is exothermic or endothermic, being spontaneous. So we cannot use the sign of delta H. We can't use it to our advantage to predict the direction of a spontaneous change. Okay, well, now we've gone to the point where we've used all of our information. And this is when the Winchesters were turned to their trusted mentor, Bobby, who's really a father figure to them, who excels at making connections and offering valuable information or new information for the hunt. So we're going to go pay a visit to Bobby so that we can start uncovering new information and therefore new variable to help us predict spontaneous change.